already started this part of synchronous machine models. I think we covered all this per unit quantities, equivalent circuits. I think we are here. I think it's better to copy these figures here. Okay, so I think we stopped here last time. Reactances and time constants of the synchronous machine. As we it's pointed out in direct X equivalent circuits for the armature, for the stator or the armature mutual inductance between the field Dunbar winding and armature is XMD, and this is the field winding, and this is the Dunbar winding, and this is for also quadrature X, armature mutual inductance and the Dunbar winding. So based on these equivalent circuits, you can find the reactances, transient reactances, subtransient reactances, and also time constants, transient and subtransient time constants. Synchronous reactances for the direct X, we have here XL leakage reactance plus the mutual reactance, mutual inductance here, mutual reactance. XQ equal to XL plus XMQ also. This is the steady state reactances. And field Dunbar total reactances, XF here equal to the leakage plus the mutual X Dunbar winding and the DX and the quadrature X. Again, the leakage reactance plus the mutual. And if we have the transient reactance equal to XL, and you have the field winding here, which have the influence in the transient period. So you have the field winding and XMD in parallel, as you can see here in this equivalent circuit. Probably we need to copy this again, but anyway, so becomes equal to here XD prime equal to XMD and XLF are connected in parallel plus XL, so you can have it here as XL plus XLF XMD in parallel. This is the equivalent. And for XQ prime, you can have the same, but in XQ prime, you have XL plus XMQ. And as we mentioned earlier, in the Dunbar winding, this Dunbar winding, the effect of Dunbar winding appears only in subtransient period. This will be involved in our calculation if we are executing like XD double prime or XQ double prime or time constant D double prime or TQ0 or TQ of this double prime. So in double prime, you can have the effect of the Dunbar winding. Otherwise, the Dunbar winding has no effect on transient period. So this is a transient reactance. You have XL plus XMQ. Right, with subtransient reactances, the Dunbar winding will have an influence here. So, for example, for this circuit, if you want to calculate the subtransient reactance XT double prime equal to XL, and you have 3 parallel inductances here. So you can get the equivalent of the 3 parallel inductance plus XL. And for XQ double prime, you have here XL, and you have XMQ and XLQ here in parallel. So you can get the subtransient reactances. Yes, here it is. XD double prime to XL plus the 3 reactances in parallel, field, Dunbar winding, and the mutual reactance. XQ double prime XL plus XLQ plus XMQ in parallel. So this is the equivalent. So this is the subtransient reactances. The time constants also, you can have the time constants in Dunbar in field in synchronous machine. We define 2 types of time constants. Time constants with the armature open circuit, and time constants with the armature short circuited. So you can calculate, for example, the time constant of the field winding if this is open circuit in one case. In the other case, if this is short circuit. So if this is open circuit, this reactance will not play any role in calculation. If this is short circuit, now we have a reactance here parallel with XMD if you look at it from the field winding point of view. So we have 2 types of time constants, TD O prime. O refers to the open circuit, without O refers to short circuit. So this is the TDO prime, and this is TD prime. The difference that the armature winding here is open circuit, open, and this is in short circuit. So if this is open circuit, you can see, of course, X over omega equal to L, time constants L over R. Time constants for such circuits equal to L over R. So for the field winding, you have, if this is, again, we need to copy these circuits here. Oh, there is no space, but so you can look at this circuit and see the time constant for the field winding here. So for the field winding, it is the equivalent here, and this is a transient. So this winding has no effect. So what you have here XLF in series with this. This is open. This is open circuit. But this will not play any role, and this also will not play any role. So the reactance over R, and you divide here by omega to get it L. So it is L over R. So this is the L in the circuit now, XLF plus XMD. And if this is short circuit, if you short circuit this, you have XL parallel with XMD, and the equivalent is series with XLF. So this is the XLF plus the equivalent of XL and XMD, and this is over B omega to get it in L. For the quadrature X, TQ O prime and the TQ prime. So TQ prime, TQ O prime equal to what? equal to this is the you have here again. This is in transient period. This is doesn't play any role in this case. So you have it here. This is a subtransient right away. Okay, subtransient again. This Dunbar winding will take place on this. So you have here the the reactance of the Dunbar winding, and you have LF, XLF, and XMD in parallel, and this is the open circuit of the armature. With the short circuit of the armature, you have the same, but you have another reactances here in parallel, which is the armature reactance, and this is for TQO prime or double prime, which is the you have this circuit XQ and XMQ. They are connected in series if the armature winding is open circuit. If it is short circuit armature winding, then you have XMQ and XL in parallel with XLQ, and you divide by RQ to get the time constant. Do you have any question? So in transient, in subtransient state, sudden change occur in armature currents in field winding and also in Dunbar winding. So this is in subtransient period. Therefore, the subtransient reactances and time constants will be used for subtransient state analysis. So this is the extensive model. If you include the subtransient Dunbar winding, and so you will end up with the seventh order model as we pointed out before. In the transient period, Dunbar winding disappear, or the effect of Dunbar winding disappear. So you have only the armature and the field winding. In the transient state, the field winding effect still exists due to its large time constant, and the Dunbar winding effect will rapidly disappear due to small time constants of the Dunbar winding. Therefore, the transient reactances and time constants will be used in transient state analysis. So this is the reactances and time constants of the synchronous machine, and this is the typical values for the synchronous machines that we have in industry. So you can see here for the hydraulic units, what is characterize the hydraulic units? What do you think? And what is the major difference between the hydraulic units and thermal units? What do you think? Ayub Al-Hurani?
Dr. speed.
السبيد. هنا السبيد ايه؟
In hydraulic slow.
Low. هنا we have high speed. What else? Any other difference?
Because of the speed in the hydraulic system, so the type of generator used there is like cylinder generator, while in high speed thermal system, then you can have the other type of generator like I forgot the name of this generator.
You mean this is salient pool?
Yes.
And this is round rotor?
Yes.
You are right. This is the salient pool generators. The number of pools is very high. It's very high. Here the number of pools is low. 2 or 4 only. So this is why the speed synchronous speed 120 F over B. So you have here 2 or 4 poles for the thermal units. So synchronous speed is high. Here we have a higher number of poles and the speed is low. So to reach to the frequency equal to 60 hertz, you need a higher number of poles here in order to get 60 hertz. Salient pole, this is the salient pole, and you know the salient pole you have XD. XD is much higher than XQ. And the air gap here, this is the Q axis and this is the D axis. This is the air gap. The air gap here is small, so reluctance is small. So the XD is high, but here you have the air gap is high, so the reactance is very low. So this is for the salient pole. For the thermal units, we have round rotor. The air gap is almost constant, and you can expect an XD approximately equal to XQ. So XD equal to XQ. So you can see here the typical values of XD, XQ, XD prime, XQ prime, subtransient reactances, transient time constants, subtransient time constants, leakage reactance, and armature resistance. So for synchronous reactance XD and XQ, you can see for the hydraulic units here, XD is higher than XQ. And here we have almost, they are the same, almost. XD equal to XQ. XD prime, XQ prime, you can see here XQ prime is almost 0. XT double prime, XQ double prime, as you can see here, transient time constants. You can see for the field winding, you can see the time response of the field winding. This is the time constants, about 9 seconds. So slow response in the field winding, you can have them here also between 10 seconds, typically 6 seconds for the field winding to respond. This is the time constant, and this is for the Dunbar winding. Time constant, the Dunbar winding is very, very fast, appears only in subtransient period. So the time here is very, very small. This is the leakage reactance, and this is the armature resistance. So these are the typical values for the industrial generators. Now let us highlight the different models of the synchronous machine. Second order model is well known. We know the second order model, which is used in transient stability analysis. You have the swing equation. This is the swing equation, second order model here. And you have here M equal to 2H. And omega here is embryonic, electrical bar torque, electromechanical, or you can have B mechanical, B electrical, and damping torque if you have some kind of friction and windage and losses here. And of course, the electrical power, which is approximately electrical torque, assuming that the speed is almost 1 per unit. This is equal to E prime Vt over XD prime sine delta. So this is well-known power angle equation. And also the power equal to terminal voltage times I cosine theta, if theta here is the phase angle between voltage and current. And this is the power angle between E prime and V. So delta is between E prime and V, and theta is between Vt and I. So this is the some algebraic equations. and E prime equal to VT plus current multiplied by JXD prime, assuming that and you have here this is E and you have JXD prime and this is VT here. So this is the equivalent circuit that you can have the second order model here. And E prime here is, these are two algebraic equations in addition to, of course, two differential equations here. So usually when we express the model of the synchronous machine, when we say second order model, we have two differential equations. But of course, we need also some algebraic equation. And you have definitely some algebraic equations here. And these are the algebraic equations of VE and E prime. And this is the second order model that you have here. And this is the phasor diagram. This is the voltage, this is the current, and this is the angle theta. And this is the angle delta between E prime and VT. And E prime equal to VT plus JXD prime times I. So this is the second order model. Well known طبعا second order model. There is no point about it. The third order model, what do you think? What do you think the additional differential equations? What do you think the additional differential equation that we need to add here? Yes. Ramadan.
Yes, is it the field winding?
Field winding, yes. Here we will add to these two equations one additional equations to describe the effect of the field winding on the induced EMF. This E prime, and this, if you still remember, now we take usually in transient stability, we assume that E prime is constant. During volt, post fault, we assume this value is constant, isn't it? We take an E prime constant. Am I right?
Yes.
In the third order model, E prime is no longer constant. We have to see the dynamics in the field winding. This is the induced EMF, comes from the field winding. So if we have transient in the field winding, if we have dynamics, if we have changes in the field current or field voltage or so, this will affect the E prime. So in addition, these two equations, we will add another equation of E prime dot. And specifically, we can say EQ prime dot. In field winding in the direct X, the induced voltage will be in the quadrature X. So the third order model is nothing but we add here the field winding equation. Change in the flux linkage and field winding cannot be neglected. So therefore, one more state equation for the third order synchronous generator. The state equation third order model may be written as, this is the first, second as usual, third equation EQ prime dot, this is similar to E there, equal to 1 over the time constant multiplied by EFD, which is the field voltage, EQ prime, XD minus XD prime ID. So this equation will be added here. We have the derivation of this equation, as we will see in few minutes. And of course, these are the three differential equations. What about the algebraic equation that support this one. How to calculate the electrical torque here, what is the EFD, and how to later we will see how to relate this EFD with the when we discuss the exciter model. We will see another equation for EFD, but at the time being, these are the three states, omega, delta, and EQ prime. These are the states here, and the following are the the algebraic equations. The algebraic equation, electric power or electric torque, expressed as VDID plus VQIQ, and this is very simple. Of course, VE equal to VI conjugate. If you can write V equal to VD plus JVQ, and you have here I, this is SE, which is VE plus JQE equal to this. So this is ID minus, minus JIQ. So in this case, VE equal to real part. A real part will come from VDID, will come from minus J times J, so it will be VQIQ plus VQIQ. If you want to calculate the QE also, a reactive power output of the generator in terms of the D and the QX voltage and the current, you can write here, this is plus, so this is VQID. And this is minus VDIQ. So you can express the electrical power output of the generator as VDID plus VIQ. This is algebraic equation. Of course, Dunbar winding, Dunbar damping power equal to, if you have D and damping coefficient, damping factor. This is not the zeta, this is the damping of the machine. So omega minus 1, omega here is in the speed in per unit. VD equal to XQIQ. VD equal to XQIQ. And the VQ equal to EQ prime minus XD prime ID. So these are VD and VQ in terms of IQ and ID. So of course you can substitute here on LVD and also VQ, and you get TE as a function of the currents, and this is no problem. So this is the algebraic equation, in addition to the three differential equation as we stated earlier. Derivation of the third state equation. This is how to derive the third equation here. And I would like to skip this part or this derivation, and definitely we have a shortened time or shortage in time. We will be squeezed in coming weeks since the exams will be earlier. So, and I would like to skip all this derivation of that equation.
Doctor, the exam even for third degree?
Sorry, I didn't hear you well.
The exams, they are moved ahead even for master's degree or for higher studies, and in April?
Allah, it seems, yes. Yeah, but there is nothing official from the university so far, but we heard, things will be shifted earlier in order to finish before before Eid. Yani 24th of Ramadan, maybe this will be the last day. But nothing confirmed. Yani we are waiting for some information about this. And this will be communicated to you definitely within a few days.
Okay.
So these are the derivation. This is the phasor diagram. And these are the algebraic equation that we have, EQ prime, or VQ equal to EQ prime and so on, and VD equal to XQ, IQ. Okay, so a third order model, by the way, is very important for us. Then we will use this model, which is this third order model, extensively in designing the field controller, or what we call the power system stabilizer. So we will focus more and more on the third order model. Fourth order model, this is another model. In the third order model, we consider only the EQ prime dot, that we implicitly saying that ED prime is, we have EQ prime and we have ED prime. When we consider only EQ prime in the third order model, we assume that ED prime is constant. There is no changes in ED prime. But if we extend this model to include also the dynamics in ED prime, we have now fourth order model. So in fourth order model is we have an additional equation. This is the EQ prime dot. This is the third order model. And we have another equation here in ED prime dot. And this ED prime dot is equal to 1 over TQO prime minus ED prime XQ minus XQ prime ID. Here you have IQ, ED, IQ, and so on. طبعا there is no field voltage in the quadrature X. Field voltage in direct X only. So we don't have here such or similar term here. So it is the same, but we consider here the dynamics in the ED prime as well. So this is the first order model, or what we call two-axis model. So we consider here dynamics in D and Q. These are the algebraic equation which support this model, VD equal to there in the third order model, VD equal to XQ IQ. But here VD equal to ED prime plus EQ prime IQ. VQ is similar to what we have in the third order model. And this is the electrical power again, equal to VD ID plus VQ IQ. You can substitute VD and VQ here. You can get out of this equation. So these are the algebraic equation that we have in addition to the fourth order model here. If you need to include also the dynamics in the Dunbar winding, we can go to basic flux model or seventh order model as we derived earlier. There's nothing but with this is the first model that we derived earlier in the last material, last handout. For certain power dynamics in the third order models, then we need more elaboration, more details of the machine. Not only the field winding, but also the damper winding. So we go to the subtransient time constant and reactances, and the flux linkage themselves can be chosen as a state variables. And as we derived this model earlier, this is a swing equation in addition to the flux linkage in direct X, flux linkage in quadrature X, and flux field winding. So this is and the damper winding also in the direct X, damper winding in quadrature X. So these are the the mechanical part of the machine, and this is the electrical part of the machine. You have here fifth order model for the electrical part and second order for the mechanical part. So it comes to seventh order model of the synchronous machine. In terms of the flux linkage, the electrical torque equal to phi d psi d IQ minus psi q ID. So this is the algebraic equation. However, the flux linkages are not directly measurable, and this is the limitation of using such model. This such model flux linkage is not measurable, and the states are not measurable here. So sometimes we express this flux linkage in terms of the currents, and we pointed out before. Also, we can express the psi in terms of Li, and then we can have the currents and the reactances. But usually, this is not used extensively, especially in dynamic stability studies, where the third order or fourth order model are enough. So this finish our handout for this part. Do you have any question? Do you have any question?
Doctor?
Yes, please.
What about fifth and sixth order?
There is no fifth, sixth order. There is no fifth order. There is no sixth order. You have second order. If you include the field dynamics, then you have third order. If you include also the dynamics and the direct X, so you have fourth order. If you include the subtransient dynamics and the damper winding, so you go for the seventh order.
Okay.
So there is no fifth order or sixth order. Okay.
Yes, Doctor. Another question I want to ask is, given that all of these analyses are peculiar to the three-phase machines, and I have seen that there are some machines that are also like 4-phase, 5-phase, and even more phases. So how you think the models will also be the same for this kind of systems? And is it possible that we are going to have a kind of a more like 4-phase machines or 5-phase machines in the future that will perhaps replace the existing machines?
Well, okay. So what you have here in real life, you have only the third three-phase machine, and all these analyses are based on the three-phase machine. Okay. طبعا nowadays we don't have 4-phase or 5-phase or 6-phase synchronous generators. You may have 5-phase induction motors. You may have 6-phase induction motor or multi-phase, maybe 9-phase induction motor. طبعا الاناليسيس will be completely different. لانه in 6 phase for example, if you have 3 phase and 3 phase winding, 6 phase is similar to have 3 phase winding and also another 3 phase winding. So you have 2 direct axes D1 and D2 and the 2 quadrature axes Q1 and Q2. So the analysis would be طبعا different. In future I don't know whether we can think about having a multi-phase synchronous generator. يعني in near future I doubt. This is so.
Thank you, Doctor.
Thanks. Any other question for the machine models, especially the third order model? Third order model, we will consider it in our future handouts or subjects. So you have, again, third order model, you have swing equation and EQ prime. This EFD comes from the field, and if we go to the dynamics of the field, we will express this EFD as another differential equation if we consider the exciter model as the excitation system, if we consider the dynamics in the excitation system. So we will add to the third order model, this is for synchronous generator, one additional differential equation, this is for the exciter. If we need also to consider the mechanical part of the governor, we will add another differential equation here, and this equation will be what? What do you think? If we consider also the governor, what would be the differential equation that would be added here? يعني we have now synchronous machine, and this synchronous machine will be considered here as third order model. In addition to synchronous machine, we have an exciter. This exciter could be added here as a one equation. طبعا الاكسايتر we have several types of exciters, but the simplest one we consider it as a first order, so we have only one differential equation, but you can have dozens of differential equations for the exciter in practical and real life. So assume that this is the simplest model. So the exciter will be considered here to get the complete model of the synchronous machine and the exciter and the governor. For exciter, we will add here EFD prime. What about the governor? What do you think, Shabab? This equation will be what? Which variable here, where we consider it as a constant as of now, will be governed by a differential equation in this case? Abdulaziz Al-Johani?
Maybe mechanical power, Doctor?
Yes, you are right. Mechanical power. Tm dot. If we consider the governor is varying the mechanical power. We consider it here as a constant at the time being, but if we consider the governor, this will be a variable. Comes from the differential equation here. You are right, Abdulaziz. So this is the third order model, and also I would like you to know these algebraic equations, which is the supplementary equation for the model. Okay, so let us close this and start now the dynamics of the field winding or the exciter or the excitation system in general. So we have here the exciter model. exciter and automatic voltage regulator. Automatic voltage regulator models. Okay. So we will see the model, general model, let us say, of the exciter and the automatic voltage regulator. And we will explain the blocks involved in this. And we will see the one of the limitations or, one of the limitations of the excitation system, which is the saturation impact, and also the stabilizing transformer. And usually the exciter has a negative gain and which deteriorate the system stability. So we add here a stabilizing transformer in the exciter, in the excitation system to stabilize the system. We will see the structure of the stabilizing transformer and the function. Simplified, we will consider here the simplified IEEE type 1 exciter model, which is the first order model that will be added to the third order model there to have 3 for the machine and 1 for the exciter. Practical exciter models also we will give you some indication about the real life exciters, which is used in power plants here in real life in general, not only in Saudi Arabia, but in real life in general. So the original function of the exciter and the voltage regulator is to provide an adequate excitation for the synchronous generator field winding. Usually, the function of the exciter is to you have here terminal voltage. We need to we need to fix, we need to control the terminal voltage. Usually in power flow studies, when we have a generator, we call it PV bus. While we can control B through the governor, we can control voltage through the exciter. So the main function of the exciter and the voltage regulator is to control the terminal voltage. If we have any change, we change the excitation, so we have the terminal voltage constant, and this is by the governor. So this is the main function of the exciter, is to control the terminal voltage here. Excitation increases for a voltage drop, and then excitation decreases for the voltage rise. Of course, this is a control. So if you experience higher voltage, then you want to reduce the excitation, and vice versa, of course. So while we are studying here the excitation, and when we want to control the system dynamics or improve the system stability, this will be done through the excitation system. We have what we call the power system stabilizer, and this is applied in the excitation system. So this is why we have to study the excitation system here, and in order to design a power system stabilizer later on. So this is the block diagram of the exciter and the automatic voltage regulator. This is the terminal voltage. You measure the terminal voltage and you compare it with V reference. And if you have any error, then this error will be propagated here, and you can control the field voltage in order to bring the terminal voltage back to its reference value. So usually you have some measurement devices or filter. So you can model the filter here as such. This is the regulator, automatic voltage regulator. first order model, you have some gain and time constant here. And definitely we have some of the saturation or limiters here, maximum and minimum. You have to control this, and this is the exciter. And this is the simulation of the saturation model. And this is the stabilizing transformer. This is the transfer function of the stabilizing transformer. We will see it physically now. But this is usually the case. You have some other signals here, and this is what we say power system stabilizer can be installed here. You can, for example, measure the speed deviation. You have, of course, delta omega dot and then, or delta delta. And you can have the, differentiator, or delta frequency, or delta power. You can measure any variation of the swing equation. When you solve the swing equation, you have delta or omega varies from delta omega, which is omega minus 1. Delta omega is omega minus 1. One is a steady state speed, or omega synchronous, and this is omega. So omega is varying due to the fault or due to any disturbance. So if you measure the deviation of delta omega and you have a power system stabilizer or controller here, this controller can send a signal here, and this in order again to change the EFD in addition to its main function. The main function of the exciter and automatic voltage regulator is to control the terminal voltage, period. But we can also, in addition to this function, we can install a power system stabilizer in the excitation model or excitation system here in order to improve the system stability. In order to increase the damping for this delta omega, we need to, if you have any deviation, so if you have such a stabilizer, you can have very improve the damping with these oscillations and any variable of those. So this is the excitation system, and this is what we meant by other signals. This comes from a controller here. So let us see the each block in details. The first block, which represents the rectifier or filter of the measured terminal voltage, and usually TR typically between 0 and 0.06. And usually this is 0. We can set it as 0, so this becomes 1. We assuming that the terminal voltage is coming here. So, but the time constant here is very, very small. The second block represents the voltage regulator, has a time constant TA and again KA. The third block is the limit. Typical range of TA is 0.06 to 0.2 second. The KA is 25 to 50. This is the gain of the automatic voltage regulator. This is typically the value, but sometimes you can have it up to 400 KA. And this is usually KA with very high values of KA, system stability becomes less, the stability margin becomes less. So usually typically KA between these values. The voltage regulation is an amplifier to error signal terminal voltage. So it is like an amplifier to the difference between terminal voltage. This is delta E here. This is V reference minus VT. And then you multiply it by this gain as if you amplify it. This is just a limiter. You need to limit the voltage here to maximum and minimum. And then you have this block, which is the exciter. what do you think the exciter in real life? Let us take the question of Abdulaziz Al-Johani first, and then we ask you about the exciter. Yes.
Yes, Doctor, if you can briefly just from mathematical point of view, for example, if I want to compute VT after this block, the filter block, what exactly am I supposed to do?
VT here?
Yes, am I supposed to multiply by the block?
Yeah, of course. Of course, the signal here, assume it, for example, X, for example, X. Okay. So this X equal to VT multiplied by 1 over 1 plus STR. So you can put it in differential equation form. You can write X plus STR X, multiply this here, equal to VT. So this one is Sx, which is X dot. So TR X dot, TR X dot, Sx equal to X dot, equal to VT minus X. So you can write X dot equal to 1 over TR multiplied by VT minus X. So this is the differential equation of that describe this block here. Okay, is it clear? At a steady state, you can put X dot equal to 0 at steady state, right?
Yes.
So VT equal to X at steady state. If you have any dynamics, if you have any change, that means that we have a delay. And for example, if you have a sudden change in VT, how the X will change? The X will change as a first order system. So the X will come as such. This is X. This is VT. And this is the response of X as a first order, with the time constant equal to TR. Okay? If TR equal to 0, that means no VT and the X will be the same, typically. There is no delay. TR here represents a delay. Is it clear?
Yes, thank you.
Okay. Now my question is, what is the exciter in real life? What do you think? What is the exciter physically? Omar?
The exciter may be some form of DC source.
DC source.
Yes.
Could be what?
It could be a battery.
Battery?
Or it could be some form of DC generator.
DC generator, yes, you are right. Small DC generator that provide the field winding with the DC. Could be static exciter, and you have also could be DC generator, could be static exciter. You have here like a rectifier. You have a rectifier here. You have a rectifier which convert from AC, three-phase AC generated from the main generator to DC source to supply the field winding. This could be. We may have also like AC exciter, not only DC generator, but AC generator, and the output of that generator will be rectified to DC to supply the field winding. So you have several types of exciters. DC exciter, AC exciter, not AC exciter. That means no, the output is AC. No, the output is AC, but this will be rectified to DC. And the field winding is DC winding. You have to supply it with the DC source, or you can have a rectifier right away from the three-phase to DC value. Since we have field winding, so we may have saturation. So we may have here a saturation factor. This is the saturation factor as a function of EFD, as a function of the field voltage. Omar, do you have a question, Omar?
Yes, doctor.
Yes, please go ahead.
And the machine itself, since we have AC exciter, so can the machine itself be its exciter? Can the machine excite itself?
Excite itself?
Yes.
And how it excite itself? What do you mean? Yani, you have a three-phase winding output from the machine, ABC, and you can take this here as static rectifier, and you have this here. This is for the field winding. So this is the case. Yeah, could be from the this could be from the field winding from the machine. Yani you can from the output of the machine, which is the three-phase AC. طبعا يعني again, of course, the voltage here is 13.8 kilovolt typically, or 18 kilovolt. So you need some kind of a transformer here in order to reduce the voltage. So you can have, yes, you can have the excitation from the machine itself.
Okay. Okay.
Yeah. And this is usually the case, by the way. And this is usually the case. And, okay, let us see here if you have a generator. You can have a DC generator. This is the synchronous generator. This is the main, and you have here DC generator. This is the exciter. The exciter here is mounted on the shaft. So you have mechanical power input, shaft is rotating, and you have DC output here, DC output for the field winding. So this is like a separate. It is not supplied from the synchronous generator. This is a DC generator mounted here, right, on the shaft. And when you have input, when the shaft rotates, then we have induced voltage here on the to the field winding. So may or may not. If you have a static exciter, then you can have the from the three-phase to the rectifier here. Is it clear, Omar?
Yes, doctor, it's clear. Thank you.
So this is the first, second block. It could be a pilot exciter, another DC generator, or a solid state amplifier for the for this. Third block represents the limits imposed on the level of the output of the voltage regulator, or limiter, or saturation limits plus minus maximum value. Fourth block represents the exciter with an output EFD. Limits can be imposed on the EFD, and you can have this EFD. You can have also some kind of limiter here. So you limit the output value. You can have here KE and TE. So this is for the exciter gain and time constant. This TE is maybe 0.05, something in that order. KE is a problematic element here, which is negative. This value is typically negative, and this is why we need to stabilize the excitation system by what we call stabilizing transformer, as we'll see later on. So the fourth block is EFD. You can have limits there. The TE and the KE, typical value of TE is 0.5, and that of KE is minus 0.05. There are two negative feedback loops, which one, first one through the saturation factor, SE, that represents the saturation effect of the excitation system, and the third one, second one, the other represents the stabilizing transformer with a time constant TF and gain of KF. You can see the the transfer function of the stabilizing transformer as SKF over 1 plus STF. So this is the transfer function of the stabilizing transformer. The TF typically between 0.35 and 1 second, and the KF between 0.01 to 0.08. Okay. Neglecting the first block, the fundamental model of the exciter can be written as, of course, you can derive the model of the exciter now. If you have such exciter, assuming that this is not there, TR equal to 0, so VT is here, X equal to VT here, if this is equal to 0. So this is VT, VR, and assuming also no, this is 0, there is no controller, so this part is out. So you have V reference minus VT going here, and this is the output of the stabilizing transformer, and then you have KA, TA, and this is the limiter, and then you have this block and feedback here equal to SE. SE is just a feedback gain. SE is a function of the field winding, which could be 0.1, 0.2, 0.3. This is a gain. So this is a scalar value. It depends on the value of EFD, and this is the scalar value, as we will see later on. If you have such a block diagram, this is the exciter. The machine, we have either the second order model of the machine, either we have the third order model, fourth order model, seventh order model. This is for the machine. طيب, with this exciter, how many states in this exciter, if we add this exciter to the machine later? So how many states will be added to the machine model? How many states do we have in this block diagram? How many states?
4 states.
Ramadan, Ali? Ramadan.
4 states.
4 states. What are those 4 states?
From each block, there is a state.
You consider this as there, Yani? You don't neglect this one.
Oh yeah, I consider this one. So without this, it's a 3.
Without this one, assuming this is, as we mentioned, this is 0. So how many states do we have for this block? Now, 3 states. After each integrator, you have 1 state. 1 state here. After this integrator, 1 state here, PFD is a state, and 1 state here. So you have 3 states. Assuming this equal to X1, and this equal to X2, and this one is EFD. Can you write هنا VR خلاص بقى VX1 خليها VR, and هنا خليها VF. assuming this VF. So these are the signal here, VR, EFD, and VF. Can we write the state equations for this? Similar to what we have done here. We take this block and we say, you know, this signal equal to this signal multiplied by this, and we multiply this and we assume that, you know, s times x equal to x dot, and we end up with this differential equation that represents this block. Can we do the same for this block? Can we write VR equal to the signal comes here? The signal comes here, which is V reference minus VT minus VF. The signal here is V reference minus VT minus VF. So this signal will be multiplied by this block to get the VR. And this VR will be multiplied by 1 STA, so VR dot times TA equal to KA times the difference here, so you can get VR dot. EFD, you can write EFD equal to the signal here multiplied by this. So this signal is VR, this signal is VR, this signal is SCE minus. So here we have VR minus SCE. So this VR minus SCE multiplied by 1, EFD will be multiplied by TESTE, SCFD will be EFD dot. So you can write the other equation. VF equal to EFD, you have the signal here, which is EFD. This EFD will be multiplied by this. So SCFD will be EFD dot. And 1 plus STF will be multiplied by VF. So you have also VFD, VF dot. So you can, of course, express when you have EFD dot here, you can replace it by the quantity given from this block. So in principle, you can write the state equation of the excitation system. For this excitation system, you have 3 differential equations: EFD dot, VR dot, and VF dot. Of course, you can replace the EFD dot from here by all this quantity. So you can have this. Okay. So this is the block diagram. Is it clear to develop the third order model here for this block diagram? I think it is straightforward. Do you have any question? Time is over. So let us stop here and continue next class, inshallah. If you have any question, so please ask. Otherwise, you can leave.